All right, stats, this is the first day of notes for Chapter 9. Chapter 9 is all about hypothesis testing, so today is our start for that. So a significance test starts with a careful statement about the claims we want to compare. So a significant test is going to have two hypotheses. It's going to have a null hypothesis that usually uses that H with a little sub-zero, and we are always using parameters, not statistics. Okay, and then we are also always using the equal sign to a value. Right, so we are still doing proportions, we're still doing means, so it would look something like this, that we believe that the population proportion is 40%, or we believe that the population average is 122, or 112, something like that. Okay, so it's always a parameter value. There's never going to be a p hat here. There's never going to be an x bar. It's always going to be equal when we do them. All right, the alternative hypothesis gets listed directly underneath it. And so that's a H with a sub little lowercase a. And it also only uses parameters. It does not use statistics. So same types of variables, p's, mu's, sigmas. Okay, we are always going to use not an equals. It's either going to be a greater than the value, or it's going to be a less than the value, or it's going to be a not equals to the value. So if our null hypothesis is that the true proportion is 40%, our alternate might be that the true proportion is greater than 40%. Or if it's a means problem, it might be something that the population mean is not equal to 112 or less than 112. Those numbers are always going to match. The only thing that really changes are the symbols between them. The null hypothesis is always first. It always gets an equal sign. All right. And then the last little point we have under alternative hypothesis is the number used, proportion or mean or other, should always blank between the null and the alternative hypothesis. They should always match. They should always be the exact same number. Okay. All right, the alternative hypothesis is one-sided when we only have, so this is the alternative hypothesis, right? So the alternative hypothesis is one-sided when we're using less than or greater than, because we're only looking at one side of that number, either lower than it or higher than it. We consider it two-sided when it's not equal, because now we're going to add up everything that's below the number, everything that's above the number. That's going to be two different sides. All right, so that's the first thing we're going to practice, is how to bring in this new thing of hypothesis and bringing them in, okay? The next thing is going to be, how do we reason this stuff? So the tests are going to ask if the sample data give convincing evidence against the null hypothesis and in favor of the alternative hypothesis. So a test answers the question, how likely is it to get a result like this just by chance when the null hypothesis is true? So there's a couple key points in here, and that is whenever we're discussing it, we are always discussing it assuming that the null hypothesis is true. And we always answer this in terms of a probability. So every time they ask you to explain what a test means, you're going to be talking about a probability, and you're going to be relating it to the assumption that the null hypothesis is true. So one of two things happens. Either the null hypothesis really is true, the mean really is 112, and maybe just by random chance when we do our sampling, we get something that is different. So maybe when they're asking us, we think it's 112, and you go, you know what, I'll go check. And you go take a sampling and you go, you know what, my mean's coming up to be 110. Well, how does that happen? Well, either it really is 112 and by random chance my outcome of 110 just happened, or it really is 110 like I sampled and the original is different, and so our result is not an unlikely outcome. So we're kind of testing things going, all right, you're claiming it's this, let me go do a sampling and then we'll talk. All right, so it's either you were right and I just got my answer just by chance, or I'm right and your answer was weird and wrong. All right, it's always easier to decide when the sample data is far away from the parameter. So if you say it's 112 and I get 110, how weird is that? How rare is that? Probably we're pretty close in the grand scheme of things to the same value. But if the null hypothesis is 112 and I get 256, we're like, wow, that's a humongously different thing. Something bigger is happening here, right? More than likely, you're wrong and I'm probably right. All right, so how do we interpret? There's going to be a p-value in here. That's just our probability number. So this is the probability of assuming that the null hypothesis is true. There is some kind of probability of getting the same or more extreme result purely by chance. So let's do the probability one. Let's say that we had a null hypothesis that was like here at 0.40. And again, it's the same thing as confidence intervals. We're going to hope that we can say that the distribution is approximately normal. We're still going to check those conditions about randomness and 10% rule and normal or large count rules. So let's say the statement is that the null hypothesis is that the true proportion really is 4%, 40%, and the alternative is that it's not. Okay, and so I go and I do my sampling and I get a proportion that is down here at let's say 8. Okay, so that's where I get mine, is at 0.08. So assuming that the true population parameter really is 40%, there is about what percentage chance of getting the same or more extreme. So if it was a not equals, I would want to add in this amount and then whatever the same amount is on the other side. So I'm 32 away, so the other side would be 72 away. So I'd be adding up all of the probability 1, probability 2, and we'd be saying probability plus probability 2 equals, right? So this is how weird it is for me to get an example like 8% when you're saying the real true proportion is 40%. So that's how we interpret a p-value. The p-value is just our proportions under the curve for what our sample look like. And depending what the alternative is, depends on whether I just color in one side and add up all the probability, or I color in both sides away from what that H sub O is. Okay. Then they're going to ask you to make a decision based on what you got. So if they're stating that the proportion is 40 and I get 8, how big of a difference is that really? So our decision is going to be based on the p-value, the probability amount, and is compared to a previously stated determined alpha amount. That's the alpha level. It looks like a little fish, right? It's a Greek symbol alpha. Alpha levels are determined or stated before the data are produced. So we kind of state at the very beginning that when I go to test this, we're going to try to be within this alpha level. So alpha levels are usually 10%, 5%, or 1%. And they're usually stated at the beginning of the problem. If they don't give you 1, we're going to use 5% as our standard if they are not stated. So 5% is our standard. Okay, so if the p-value is less than the alpha level, that means that I am very, very far away. And I'm going to say, I think what you're saying is in the middle is wrong. So I'm going to say, based on my p-value, because it's less than the alpha level, we're going to reject your claim that it really is this, meaning we do have convincing evidence against the null hypothesis, and then we'd have to say what it is in context, that the true mean proportion of students that agree with this statement is 40%. Okay, so we believe it's not 40%. Because the p-value, and then the second statement is the other way. If the p-value is greater than the alpha level, we fail to reject H sub O, meaning we don't have convincing evidence, right? Because now our p-value is pretty close to, is bigger than the alpha level. So let me give you an example of that. Let's say we have our amount, we have our claim, this is where H sub O would go, okay? And I end up with a probability on a less than alternative, so we have an HA, and I go and I add up all of this amount and I get a p-value that is equal to 0.037. So I'm going to make a comparison between the p-value and whatever the alpha level is that they gave us. And we would say that the p-value, let's say that we're working with an alpha level at this one at 10%. So I would say that the p-value of 0.037 is less than the alpha level of 0.10. And because it's so much less, it's only a 3.7% chance of me being at this H sub A level or less, right? I think this is a very rare event, so I'm going to call that I don't think your HO is really the true amount, because if I was sampling, it's very unlikely I would be this far away from the true mean of the population. Okay, and then the other one is just the opposite. I have a 0.037, same p-value, same picture, right? And basically they're saying, hey, if you are under 10%, so this is where the 10% would be. If you are under 10%, we're going to call BS. We're going to say that I don't think your H sub O is true. And in this case, if I ended up right here where this is where the 10% is for alpha, and let's say this time I go and I calculate my probability and it's less than, and I end up being right here. And now my p-value, let's say, turns out to be 0.18. Well, now 18 is more than the line we set up in red. So now we're going to say, I'm not far enough away to really call that your H sub O is really wrong. I'm kind of not past that borderline where we said it's definitely a lie if I retest here. Okay. Now, honestly, nothing is really a lie here, right? Because it's all just whatever the claim is and what our sampling showed. So there's always a chance that we could be wrong here. We're just going with the probability numbers of saying it looks like it's looking this way. So if the p-value is greater than the alpha level, so in this case, p-value of 0.18 is greater than 10%, we would say we fail to reject that the null hypothesis is really that middle number, meaning we don't have enough convincing evidence against that number at HO being wrong. We think it can hold. We think we'll take our value and say it's not far enough away for us to claim BS that it's not the same, okay? So that's basically our theory, and it's a lot of logic. We'll go through it several times in class so that you get the hang of it. Okay, the last item here we're going to talk about is statistical significance. If the p-value is as small as or smaller than the alpha, we're going to say that the data we collected, our sampling data, is statistically significant at that level. So that was the first case, right? So that is any time that we reject H sub O, we're going to say that that is statistically significant evidence. That's why we're rejecting the null hypothesis and saying we don't think that original claim is true. So small p-values are evidence against the null hypothesis because they say that our sampling result is unlikely to occur when H sub O is true. So large p-values don't give us evidence, enough evidence against the null hypothesis to say that it's false. All right, so let's give you just an example of what we're going to expect you to do on day one. Day one, we're really going to just focus on you writing the hypothesis statements using the right symbols, explaining what a p-value means, and then telling us what your decision would be. So that combination of checking the p-value against the alpha level. Okay, so that's all we're going to check today. So the first one is, it says write a hypothesis statement for the following. After sampling 100 Hart High School students, seniors, the average number of classes taken per term is approximately 5.1 classes, right? So this is our sampling amount. Do we have convincing evidence that the average class at Hart High School is less than 5 classes? And then here's our alpha level. All right, so this is not a proportion problem, this is a means problem. So we've got mu equals mu equals. And the first one is we think that the average is, do we have convincing evidence of less than? So I'm going to change this equals at the bottom to less than. That's what the claim is. That's what they're asking me to check. So do I use 5 or do I use 5.1? Okay, so what are they asking me to claim, right? They say, do we have convincing evidence that it is less than 5? So it's less than 5 or equal to 5. This just happens to be my X bar that you would have started with to build your confidence interval. Okay, so you're always going to look for, do we have convincing evidence? That's the number you're going to use on your H sub O and H sub A. All right. All right, so then it says after completing the hypothesis test, our p-value is calculated to be 0.025. How would you interpret this p-value? So we go up to the second part where it says interpreting p-values. That would be up here, and it says assuming H sub O is true and state what that is, okay? So we're going to start with that. It says assuming that students, that Hart High School students, Hart High School senior students have 5 classes, right? So we're going to start out with that. Then we're going to look at the next part. It says, assuming that that's true, there is a blank probability. There is a blank probability. There is a, what was our probability that they gave us? 0.025. There is a 0.025 probability that, okay, back up to the top where we're describing it. Up here, of getting the same or more extreme result purely by chance. Okay, so we are going with how would you improve? There is a 0.025 probability that our result of 5.1 would happen just by chance. Okay, so what would we decide? Well, our decision now is going to be comparing the p-value to our alpha level. So comparing the p-value to our alpha level, we would say since our p-value is, which is 0.025, is less than our alpha level. What was our alpha level? 0.05, right? So this is less than. Is less than our alpha level, and you can use the symbol here if you want, our alpha level of 0.05. What happens when p-value is lower? We reject, goodness, I cannot spell. We reject the null hypothesis that Hart High School seniors have 5 classes on average. Okay, would this decision be considered statistically significant? Anytime we reject the null hypothesis, it is considered statistically significant. So we would consider our results to be statistically significant. Since our p-value is less than the alpha level. Okay, so those are the main things we're going to be practicing, is writing out those 3 parts of the sentence. A lot of the stuff that we just did from confidence intervals are going to copy over, so don't forget that. We're still going to be checking those same conditions. We're still going to be using that same sampling terminology. All right, that's it for today.